Okay, guys. So this is the last week, or I would say week 12 of the process modeling. Okay. This is also the last week that we will go into the last week for the lecture for the process modeling and optimizations. Okay. The unit is called process modeling and optimization because at the time when I first joined, at the time Professor Alex and Associate Professor Farouk, they are the one that make the curriculum for the process modeling. So the process optimization was included into this unit. But I think the process optimization is actually by itself is a big area to be covered. So that's why it is impossible to actually cover the whole materials for the process modeling and the process optimization into 14 weeks of unit, because process optimization is also a big area by itself. Okay. Actually, Dr. Howe and Dr. Vignesh are an expert in the process optimizations area. So in here, we just give you a little bit of introductions into this area. Basically, what is the process optimizations about? Okay. So optimization is a specific method to determine the most cost-effective and efficient solution to a problem or design. Normally, chemical engineer researchers or chemical engineer, they would use optimizations into their problem. It has been widely used in industry as a tool for decision making. It has also been used to solve many problems in design, construction, operation, and analysis. The book that we are using for these slides are the main book that is used. It's coming from US. So Thomas Edgar, Himmelblau, and Leon Lesden. Himmelblau, for example, he published a book on the mass and energy balance. I think that I use a lot when I was in my undergrad. I think some of the questions that some of you asked in the beginning, for example, about the pound mole, the gram mole, the kilogram mole, the explanations I took from the book of the Himmelblau. Okay, so this book is I think by the time that the book that we use in here is the second edition. I think now that David Himmelblau is already no longer. I think he is already passed away. Okay, I think that Thomas Edgar and Leon Lesden is probably already an emeritus professor. So what optimization is all about? So it's in a typical engineering problem. What we do is because we do a modeling, so a process can be represented by some equation or experimental data. Then we have a single performance criterion in mind, such as minimum cost. The goal of optimization is to find the values of the variables in the process that yield the best value of the performance criterion. A trade-off usually exists between capital and operating costs. The described factors in here is process or model and the performance criterion. So the process itself, you make it into an equation. So that's why it's called modeling. And then whatever you want to optimize, if let's say you want to optimize the costs associated with that particular process, you want to lower the cost, or if you want to make it, if that particular process associated with something that comes with the cost, then you want to minimize the cost for the particular process. If that particular process containing a profit, so you produce something like products, and it comes with the raw materials and with the utilities to be accounted with that particular process, then you can use it to optimize, to maximize the profit for the particular process. So this is also related with what we did in the when I go into the first lecture. I show you, I illustrate you an example of the model predictive control, right? So that model predictive control basically embed some optimizations in in the way that it's adjusting the PID control. So it is one level higher than the PID control. So why we want to optimize? Because these are some of the reasons. We want to get the largest production. We want to get the greatest profit, the minimum cost, the least energy use. In plant operations, for example, we want to have an improved yield or reduced yield of contaminants, reduce energy consumption, higher processing rates, reduce maintenance costs, less equipment wear, and better staff utilization. The best way for us to understand is always going into the insulation. So for example, the insulation design in here will give a classical example of the overall cost saving. Okay, so why we bother to use an insulation? Because if we use an insulation, it will reduce the heat loss. So meaning that whatever the process is, we can reduce the heat input into the particular process. However, the insulation material itself associated with the cost. Now, let's assume that the bare surface of a vessel is at 700 degrees Fahrenheit with an ambient temperature of 70 degrees Celsius. I think I need to go and revisit this again. This is probably 70 degrees Fahrenheit. I need to check again whether this is a typo or not, okay? Because normally if we use a SI unit, then we will use SI unit consistently all over the problem. Now, the surface heat loss is given as 4,000 BTU per hour feet square. If we add 1 inch of the calcium silicate insulation, the loss will drop to 250 BTU per hour feet square. At an installed cost of $4 per feet square and a cost of energy, the saving of 164 per year per square foot will be realized. So this is basically saying that for a certain insulation thickness, then we will be able to get a particular rate of saving, basically. Okay. So then the thing that we want to use is basically a simplified payback calculation. So if in order for us to recover the cost of the insulation, then we will need about 9 days. Okay. So, however, as the additional inches, the thickness of the insulation are added, then the increment must be justified by the saving. So how do we do that things? Basically, these are the things. So these are the plots that are giving you an idea of the cost as a functions of the insulation, because the cost increasing because the more layer of the insulations you give, then the higher the cost associated with getting that insulation materials and installation of that insulation materials, right? However, at the same time, when you increase the insulation thickness, then the loss energy will be lower. Okay, then you will ask me, why, sir, this one is coming not as a continuous line, but as a point in here? Because you can only buy that insulator in a certain thickness. So let's say that the thickness is coming at 1 inch. So meaning you can add only the thickness at an incremental of 1 inch. Okay. So if 1 inch, then you can add on only 2 inch. You can add on only 3 inch. You can add on 4 inch. So meaning you cannot have a continuous line, because when you assume that it is a continuous, meaning that it can be added as 1.01, 1.02, 1.03, 1.04. So that's why in the optimization problems we come across many different variables. So this variable in here is called a discrete variables. This is not a continuous variables. Okay. On the other hand, the cost of the lost energy can come continuously, because it comes as a continuous it can be defined as in terms of the continuous value. Now, after you see this kind of graph in here, that means that your total cost curve will be the additions of the cost of the insulation with the addition of the cost of energy. So if you add this with this, you will reach this height. If you add these two, at one point you will have a minimum point here. Okay, then eventually it will increase again. So from this example, you can easily see that the insulation thickness related with the minimum thickness for you to gain the best compromise between the cost of the insulation and the cost of the lost energy is associated with this thickness in here. Okay, so this is where the first principles of the optimization came. Did everybody get it? So in here it's given in the increment is given in half-inch increments for the insulation. Okay. Did everybody get it up to this particular point? So this is quite important because later on when you go to industry, then you will come across this kind of things. Okay. Another example will be the optimal operating conditions of a boiler. Okay. So in the boiler, you have some variables to be played with. So meaning that you can play with the air to fuel ratio. However, the adjustment in the air to fuel air ratio will have an implications to the thermal efficiency, and I mean it will also affect the amount of the fuel that is wasted out from your systems. So how did we go in that thing? We have a look into this graph. I think you can read these things by yourself. You can read the details by yourself, but more important thing is we focus mostly on the figure in here. So you see that the x-axis in here is showing the increase of air to fuel ratio from 0 to 2.0. Okay, so if we increase the air to fuel ratio, the thermal efficiency will increase in the beginning to reach its maximum, and then it will decrease a little bit. Okay, in terms of the emission, we have two emissions. The first emission in here is the hydrocarbon emission that will be reduced when we increase the air to fuel ratio. And then we also have, unfortunately, as we increase the air to fuel ratio, we will have an incomplete combustions. I mean, in terms of the nitrogen oxides. I mean, if we increase, we put in more air, that means we also will have an extra side reaction in terms of the nitrogen, because air contains oxygen and nitrogen, right? So meaning there will be some NOx that will be released also from the in the gas product. So in here, if our objective is to achieve the optimum thermal efficiency, the maximum thermal efficiency, then the best points will be stopping at this particular point, okay? Because this will be related with the minimum emissions for the nitrogen oxide and the hydrogen emissions in here. Okay. Of course, this one is an ideal situation. In most situations, it's probably not going to be an ideal situation. Okay. Now, the another feature of the boiler operation is the widely varying demands caused by the changes in the process operation when unit startups and shutdowns. So what we can see in here is that the boiler in here cannot be operated continuously from this one is basically showing the fuel input with respect to the steam output. So a boiler can only be started at this particular point at the fuel input in here, where it will start generating the steam output at this particular point. Depending on how we operate the boiler, we may have a linear response and the non-linear response. So there will be a transition from the idle conditions to the conditions where the fuel input start on taking at this particular point. That's why we don't have a continuous line that operates from the point of 0 to the points where the boiler start producing the steam output in here, basically. Okay, so that's in the real world situations, we have the situations where whatever we put in the model will not be able to reflect what you have in the real situations. So that one is described by the things in here. Okay, so that's why we show in here that the boiler cannot be operated continuously all the way down to the idle state. Instead, a range of the continuous operation will exist for a certain condition, then followed by the discrete jump to a different set of conditions may be required if the demand changes. Then we have another example in here, which is related with the optimum distillation reflux. Okay, back in the old days when the cost of the energy were very low, the objective was to maximize the separation using whatever the energy is. However, I think now these days, I think energy costs start on becoming more expensive because the population is increasing, and then the energy resources they stay the same. Okay, so now if we want to conserve the energy, that means we have to minimize the reflux ratio. So we will go into this particular graph. We will see. So in terms of this graph in here, you can see that the x variables in here depending on the reflux or the heat duty. Okay, so there is an associated things with the time that is put in here. So if the cost of the heat is low, then we will have this particular curve in here. If the cost of the heat is high, then this one. Then this will be the value of your products. So in terms of the profit, that means your the value of your product. So whatever the value of your sold product minus the value of the heat that you put in to operate your distillation column. So if the value of your cost is high, that means your optimal point will be operated in here. If your cost of the heat is low, then the optimal point will be here. The curve in here is mainly just showing you the difference between the value of the product with the cost of the heat. Okay, for the two cases. So this one is for the low fuel cost. This one is for the high fuel cost in here. Now, after we go and look at the examples, at the basic example of the optimizations, we will go into three categories. We will go into what are the characteristics of the optimization problems. What if the problem is called an optimization problem, basically what are the common features of the optimization problem? So every optimization problem will contain these three categories. At least one objective function. We will have an equality constraints and also an inequality constraint. So the categories 2 and 3, they normally constitute the model of the process or equipment. The category number 1 is called the economic model. Okay, so by a feasible solution, meaning that we have a set of variables that satisfy categories 2 and 3. Okay. However, the optimal solution is the set of the value of the variable that satisfies the component categories 2 and 3 and also provides an optimal value for the function in category 1. In most cases, the optimal solution is the unique one. In some, it may not be the case. This is basically showing you the area where you can operate. So, for example, in here, it has to be inside this. This is nonlinear inequality constraint, so you can only operate at the area within this that is bounded by this nonlinear inequality constraint. But then, if you also have a linear equality constraint, meaning that you can only operate in between these two, this. So whatever the optimal solution is, that can only operate in what in this particular line. Okay. So it's important that there is no residual degrees of freedom among the variables in categories 2 and 3. If there is no residual degrees of freedom in the variables in categories 2 and 3, then optimization is not needed, because that will be a unique problem. And then we have another two variables in here, which is MA and MI, which is the number of independent consistent equality constraint and the number of independent inequality constraint. So if the number of variables whose values are unknown is equal to these two variables, then at least one solution exists in components 2 and 3. Multiple solutions may exist when models in categories 2 and 3 are composed of nonlinear solutions in nonlinear relations. If a unique solution exists, the optimization is needed to obtain a solution, since the unique feasible solution is by definition the optimal solution as well. Okay. If more process variables whose values are unknown exist in category 2 and then the independent variables, then it's called underdetermined. Okay, so that means the model has an infinite number of feasible solutions. So the objective function in category 1 is used as the additional criterion to determine what is the best solution. If, on the other hand, we have more equations than the independent, if the equations contain more independent equations than variables, then it's called overdetermined. Okay, so one of the examples is the reconciliation of the process measurements for a material balance. So what we can do in this case is just to minimize the sum of the errors of the set of equations. This problem normally belongs to the set of the problem we call as a regression problem. Okay. Now, if we convert all those problems into a mathematical form, then we will have this minimize fx, which is the objective function, subject to the equality constraint and inequality constraints. Okay, x is a factor of n variables. Hx is a factor of equations of dimension m1. Gx is a factor of inequalities of dimension m2. Total number of constraints is m is equal m1 plus m2. In optimization problem itself, we can classify to many different type of a problem. So it can be classified as a topological versus parametric. Okay, I will not go into the detail on these things. I think you can read through these things by yourself if you want. I will add on when I see that the optimization problem is something that is important. And then we can also go into classify it as an unconstrained optimization and constrained optimization. Constrained optimizations, unconstrained solutions will be, meaning we don't have another set of the equations again to constrain this particular function. And then we also have a linear programming versus non-linear programming. So in linear programming, then everything will be in the linear form. In non-linear programming, we have something that are not linear. And also we can differentiate in terms of the convex function or the concave function. So convex function, it means it's going down, so that we have a minimum. For the concave functions, it will go like this, so we will have a maximum in our function. Okay, and then like what we showed earlier, we can have a continuous optimization or we can have a discrete optimization. If we have a mix of the continuous and the discrete variables in one problem, that will be something we call a mixed integer optimization problem. Okay, so this one can be represented, for example, by the optimization of the distillation column, which involve the variables such as temperature, that is continuous, and the number of the tray on plates. So the number of the tray on plates can only come in the discrete. So 1, 2, 3, 4, 5. It cannot come in the variables like 1.1, 1.2, 1.3, 1.5, right? And then we have something else again we call the single objective versus multi-objective optimization. So the optimization problem that contains only one objective function is called the single objective optimization. If we have different variables that you want to optimize, then it's called the multi-objective optimization. And then if we continue again, we have the local search method and the global search method. So something, a local optimum, for example, something that is optimum, that is minimum at this particular point one, it may not be equal to the global minimum. So global minimum in here is 2 in here, for example, right? So that will be a different method. The different algorithm are available, but you need to make sure to know that which one is it that you are using. Is it a local optimum search, or is it a global optimum search method? And then it can be something like this. Okay, so deterministic optimization, stochastic optimization, or a combinatorial optimization. So the one that we cover in our process modeling so far is only a deterministic problem, meaning we don't put a probability into our variables. So for example, Dr. Howe can do something related with the stochastic problem, meaning he will do something like a Monte Carlo simulated annealing or a generated algorithm. So we are instead of just doing something like precisely using deterministic, we put in a chance of the variables not behaving the same like what we predict before. So in terms of the variations, if the variable A has a variation from A to a particular point, from a particular 1 to 3, for example, 4 to 5, what will be the effect to the other variables? That is something that can be done using this stochastic optimization problem. Okay, we will not cover all these things because this will be much more complex than what we are dealing with in the problem that has been given. So if we go and look at the chart for these optimizations, then optimization can be divided into two problems, continuous and discrete. The discrete can be divided into a problem of integer programming, mixed integer nonlinear programming, mixed integer linear programming. The continuous variable itself can be divided into differentiable or non-differentiable. The differentiable one can be divided into 3 subsets. The non-differentiables can be differentiated into a 2 subsets again. Later, if you are interested to do some research on these things, you can consider to do a project with Dr. Howe or Dr. Vignesh. Okay. How do we put in example on here? So example that we have in here is the optimal scheduling. So this is basically giving you the table, giving you the materials, the possibility of the materials to be processed in plan 1 and plan 2, profit 1 and 2, A and B in here. So for plan 1, it will produce this material. Plan A, it can produce this much of the material. Okay. For plan A, it only produces the type 2 materials for this much. Now, you want to solve the particular problem of how many days per year should each plant operate processing each kind of materials in order for you to maximize its profit, for example. So this is basically giving you we are basically illustrate the problem of how to make a mathematical formulation of an optimization problem. So the objective functions will be this one, TA multiplied by the NA. So this will give you the profit associated with the productions of material A from plant material 1 from plant A, and so on and so on, because we have 4 different. Now, the equality constraints is basically related with these two, because the time that each of the plant can operate is only 365, and then the plant B can only operate to produce material 1 and material 2 for 365. So whatever the mathematical problem is, it has to be realistic, meaning that it has to fit within the real world situation. Okay. The other thing that we need to put in is that we must have a non-negative value of the T. Okay, and then the limitation on the total amount of material too that can be solved is also related with this one as well, for example. Okay, the solution or limitation on production rate also can be specified. So we need to put in a value. Therefore, to find the optimal T, we need to optimize A subject to constraint B to G. So this will entail what the optimization problem cost is. The other example that we have in here is the material balance reconciliation. If, let's say, we take in different measurements, for example, for B, we have we took at 3 different times. The mass rate is this, and same for C, we take at 3 different times. This will be the mass rate. Okay, so in essence, if we want to minimize the sum of the square of the deviations, then we need to use these particular equations. If we differentiate this with respect to MA, and then we will get an optimal value of MA of equal to 82.4. This will be the same with the result obtained from the average measured values as well. Okay, so next we go into the feature of the optimization. So the optimization problem can also be converted to a suitable form according to our convenience. So instead of solving the minimization of fx, we can instead solve the maximization of the minus fx in here. Okay, that may make it easy in some cases. Okay, these are something that are important that you need to know. For example, that the first derivative of the objective function is 0 at the optimum point, which is not true for all cases. Right? For example, if you have a limitations within A and B, so meaning you the minimum point will not be at this particular point. It's going to be in here, for example. Maximum point will not be at this particular point. Maximum point probably will be at this particular point. So it is very important that you inspect the optimization things very carefully and avoid to use a premature conclusion. So these are the six steps used to solve an optimization problem. You need to start with the analyze. We determine the criterion for optimization and specify the objective function. And then using the mathematical expression, develop a valid process or optimization or equipment model. Okay, include both equality and inequality constraints. Okay, you can use a well-known physical principles. Identify the independent and dependent variables to get a number of degrees of freedom. If this one is too big, then you break it up to manageable parts, or simplify the objective function and model. Then apply a suitable optimization technique to the mathematical statement of the problem. Check the answers and examine the sensitivity of the result to the changes in coefficients in the problem and the assumptions. So that will be all for my process optimization part of the lecture. Is there anybody have any questions on this particular part? Clarence, Daniel, James, Jason, Michael, Taha, Usman, Rachel, Selena, Tiffany, Yusi, Mongyo. Anything that you guys want to ask me before I move on into the other into discussing your take-home assignment 2, basically. If that is enough, then I will stop the recording now. Okay, I hope you get something from this one. Okay, I'll stop the recording first now. I'm not recording the discussion. Where is that one? before I stop the recording.